We've talked about access stratum and non-access stratum, and you must be wondering what the heck these things are. But as the name kind of suggests, I think you've got an idea what it is, but let's quickly cover that. We have this architecture, we have this Mehmet, this mobile, this user equipment sitting down here and communicating with the network. Now, when Mehmet communicates with the network, it communicates with the base station, and this communication is called the access stratum. And that is what access stratum is. And it includes data radio bearer, and can be multiple, and signaling radio bearers. And as we had seen in the previous slides, there are three logical signaling radio bearers that are existing between the mobile and the eNB at the maximum. I mean, so we have three of them. And the protocol and the main interface for communication is called the radio resource control that goes over the signaling bearer. So these are all the signaling messages that are transmitted between the mobile and the eNB. These are kind of the most important messages that you need to know from a systems perspective when the mobile is communicating to the base station. So that's your access stratum. And your non-access stratum is actually your communication between the mobile and the MME. And this is all the signaling messages that go between the mobile and the MME: authentication request, authentication response, signaling mode command, and we'll cover some more of these, and also setting up PDU context requests. So these are all the messages that are going between the mobile and the MME are called non-access stratum. Keep in mind that non-access stratum does not include the user plane IP packets that go over DRB and go to the serving gateway. So that is not part of NAS. NAS, or non-access stratum, is mainly the signaling between UE and MME. All right. So we got this squared away, and you will see this use of term AS and NAS quite a bit in the specifications. Another concept that we have used during these slides and in the attach procedure, we talked about two different messages, and we are coming now trying to provide you the secret as to why there are two separate messages. So there is this concept in the NAS level which is called mobility management. And the mobility management is so what is mobility management in LTE? So it is concerned with the UE's registration state. So are you registered? Are you attached or not attached? Are you registered? Have you been authenticated? Are you really Mehmet? And those kinds of messages and that kind of a state at the NAS level. So that is the mobility management part of the NAS message of the NAS state between the mobile and the network. And there are kind of two main state. There is a mobility management state machine that runs both in the MME and the UE. And as you can see, it's the two main states are whether the mobile is deregistered. So when you come in and you haven't been authenticated, and you haven't been authenticated with the network, you are essentially deregistered. And then when you have been authenticated and you prove that who you really are, that you are registered. And I mean, the specification goes into a lot more details as to when these transitions occur, but for our purposes, we will not go beyond this, the fact that you end up having two different states. And when you are really authenticated, you've basically gone into a registered state. Example of these EMM procedures, and what is E standing for? E is actually enhanced mobility management, and the reason why we've used enhanced mobility management is to kind of separate it out from the 3G specifications where MM was used. So MM is already taken by 3G 2G actually, and it's actually used for the CS domain part of it, that is your voice domain. as we said, LTE is only PS domain, is only packet domain, and we use EMM for the state machine for the LTE packet domain. And so that's the E. And some of the examples of the EMM procedures are attach, authentication, security mode command, GUTI, which is your globally unique temporary identity relocation. So all these messages, tracking area update, and we'll cover some of these in the slides later on, are all mobility management messages. One thing to keep in mind is that this service request, which we will cover when we cover idle states and connected state, which is used to go from idle to connected. That means when the UE is not really communicating till when it starts communicating. This is actually an EMM, a mobility management message, and not session management, which is the next slide that goes into. So keep that in mind, and that is a confusion that a lot of time comes about in everybody's head, whether service request is actually a mobility management message or a session management message. It is a mobility management message. And for each mobile, there is an MM context in the MME. And then the most of the MM context consists of the security related parameters, the keys and the counters. The MM state machine runs independently in MME and UE. I mean, so they both are running independently, but they are in some way synchronized. I mean, sometimes you can get into non-sync cases, but if your protocol is working correctly, these are synchronized between the UE and the MME. Now we get into the session management. So session management has to do with UE's connectivity. That is the UE's data transfer through the network, and that's the bearers. So the bearers that we've been talking about, the data radio bearer, and of course, sorry, the bearers here are the NAS level, and that's the EPS bearers that we talk about, and that's the session management state in the NAS level. And it is, again, as we kind of had for the MM, there's a state machine in both the MME and the UE, but ESM, or the ESM states, again, we have the E word in here, the enhanced, is for each EPS bearer. So right now we have only looked at one bearer, which is being set up, and all of the IP traffic of this bearer flows between the mobile and the network through this bearer. So for each EPS bearer, there is a state machine, and the two main states are whether there is a context for the state, whether it's active or inactive. And of course, when you don't have a bearer, you don't have a context, and when you have a bearer, you have a context, and you can modify that bearer also. So some of these procedures that are there for ESM are PDN connectivity requests. That means please connect me to the internet, or another message for that is also, it's also called the activate default EPS bearers. And then you can also have some dedicated bearers, and some of that will come about in the QoS when we start looking at it, and that's where we start seeing why you need more than that one bearer that we had set up all the way between the mobile and the P gateway. And the ESM context includes the context for all the active bearers and also the QoS parameters, and this is what's kind of in the mobile and the network. So the MM and the SM relationship. So how are they related to each other? There are separate NAS messages for mobility management and session management, and this is the reason why the mobile sends two messages, attach request and PDN connection request, and not just one message, because the state and the state machine in the MME has been designed to be separate from each other. There is a little bit of history that comes in from 3G, but we won't go into that at the moment. But keep in mind that the session management is kept aside from mobility management. And actually, when we go into 5G, we will see that this takes on some other implications also, where not only are the state machines different, but then the network elements or the processing is done in two separate nodes in 5G. And but for that, you have to wait for 5G specifications to complete. But just a hint that what's coming down the line. The EMM and the ESM contexts are stored separately in the MME. LTE has this concept of always-on IP connectivity, and what this really means, and you probably may see it somewhere in the specification, is that the moment the mobile attaches, a default bearer is set up for the UE to have connectivity, to have IP connectivity. Let's look at it that way. Now, for the UE to be in the registered state, the mobile must have at least one bearer context, or must have what's called the default bearer. So that's the bearer that gets set up right at attach. So for a UE to be in EMM registered, there is a connection with its SM state. And it also actually goes in this way, since it's an always-on IP connectivity, is when you remove the last bearer, when you get rid of that default bearer, so you can't send an IP packet back and forth, you go into a deregistered state. So in LTE, your MM and your SM states are kind of coupled because of the reason that the design has been for an always-on IP connectivity. And so you have this kind of a relationship. One thing to keep in mind is that what we are talking about here of an always-on IP connectivity is for LTE specifications up to release 12. So if you are looking at LTE specifications, one of the things is bear in mind is that better not to look at release 13 specification, because a lot of changes came in from IoT, where there were some designs that said that I didn't need an always-on IP connectivity. So if you look at release 13 specification and you look at these this video, you'll be saying that I'm lying. I'm not actually lying, but I'm telling you the truth for until release 12. So that's just keep that in mind. And then the ESM procedures can only be performed when the EMM context has been set up. So obviously we are doing a PDN connectivity request, right? When we are sending an attach, both of these are being done at the same time, but the bearer setup only occurs after the authentication has happened. So once some kind of a security has been set up, the EMM context has been set up, that the bearer setup procedure really goes ahead, and you can go back and look at the signaling setup, and you'll be able to confirm that is actually true. So there is, as we said, there is coupling between the mobility management and session management in LTE. Just a quick look at what these message formats for mobility management and session management look like, because there are a few Wireshark captures, and you may want to figure out what are these messages looking like. So if you look at the EMM messages, the format is given here is that you have a protocol identifier which has got this 4-bit value, and if it's 0111, this is enhanced mobility management message, and this comes with a security type of 0. So the first 4 bits are security type, the next is EMM, and then the message type. So what exactly this is, an attach request or attach response or a tau request or whatever is a message type, and then the rest of the messages. So this is the format for a non-secured EMM message. Now for an ESM message, we actually have the protocol discriminator over here, which kind of parallels that, except that with a value of 0010, this is ESM. So once you see this value, you know ESM. But then the first field over here is the bearer ID. So EPS, EBID, as we've been calling it in all of these. So if when we set up bearer, the very first bearer data bearer that was set up, which was 5, this is the bearer ID. It doesn't have a security header. There's a protocol transaction identifier, and then you have this message type, which can be an activate default bearer, or activate dedicated bearer, or modify default bearer or dedicated bearers. So you have these things, and then you have the rest of the ESM message. And you look at this, and you must be going, hey, can I not encrypt an ESM message? What does this mean? Because the encryption header is only there for the EMM message. All right, but you can, and this is how it gets done. It's a little bit screwy in the way it's been specified, and if you're sending a secured message, that means either it is encrypted, it's either encrypted or integrity protected, or one of the two. Typically, most signaling messages are encrypted and integrity protected. So you will have a security header type which says that it is 10, and which means this is both encrypted and integrity protected. And obviously, once you have the security type, this second field over here actually has to be EMM. Otherwise, you can't have a security type. You would have a bearer ID, and that's not a bearer. So the very first thing it says, this is a security type, encrypted, integrity protected. The first part of it over here is the authentication code. So this is the integrity protection, so which protects everything from including the sequence number and whatever is a message over here. So that is what that is where you have the message authentication code. And then the message over here, this message can either be an EMM message or an ESM message. So if you want to send an encrypted ESM message, you will actually first put an outer header which first says that this is an EMM message, but then say it's encrypted, integrity protected. But inside there, what you have coming in, your encrypted message is actually an ESM message. I don't know why it was done, but this is the way the protocol works, and this is the way the format of packets is. So an ESM message, which is encrypted, comes inside an outer header, which says that this is an EMM message. And people have written protocol states, and it works well. So we don't need to bother about that. Let's look at the protocol stacks. We will look at the control plane protocol between the mobile and the MME. And on the radio side, the most important protocol that is used between the mobile and the network, at least from a systems perspective, is this RRC, is this radio resource control. So this is the main control interface, and this is the main control protocol that is running between the mobile and the mobile and the base station. You do have lower layers that are obviously providing support, and if you're a radio geek, you probably are spending half of your life kind of figuring out how these things are working. But for us, we will do a quick go through them. The PDCP layer, or the packet data convergence protocol, actually is mostly putting a sequence number and is mostly used in the user plane side of it. The same protocol we'll see also comes in the user plane side. The radio link control is doing segmentation and reassembly, so it takes a big packet, breaks it down into smaller ones, and reassembles it on the other side. It does window flow control, and it also has two different modes. One is the unacknowledged mode. That means a message that is kind of sent over the radio interface doesn't get acknowledged, so it doesn't wait for an acknowledgement to make sure it's going through. That's typically used for DRB. So the UAM mode is used for DRBs, and the acknowledge mode is the one that is used for SRBs, because signaling messages, you better be sure that it's going through. DRBs is like, your IP packet doesn't make it, you'll retransmit, I don't care, or you'll get a little bit of a blip in your voice communication. The medium access control does the access to the channel, and the main part over here is scheduling. I mean, that is the bread and butter of how your radio resources get used well. And the physical layer is the one that is doing all your modulation and MIMO and all that good stuff that if you're a radio guy, you really jump up and down about. But for us and for these lectures, I think we'll mostly keep at the RRC level point of view. And then on the side between the base station and the MME, we have the protocol, which is the S1 application protocol, which is used for communication between the base station and the MME. For example, any messages that the mobile has sent, those NAS messages will go over S1 AP, or initial context requests, hey, go ahead, set up the radio bearer, which we've looked at this kind of, are all S1 application protocol messages. It runs over a protocol stack, and the transport layer protocol is SCTP, is stream control transport protocol. I mean, in the S1 AP primer, we'll just cover one level deeper what this is. For all practical purposes, you can say that this is kind of equivalent to TCP. I mean, so you have a transport protocol which is SCTP running over IP. And then, of course, the main, the NAS, the non-access stratum communication is between the mobile and the MME, and this is used for example, for authenticating the UE or for doing tracking area updates. So these are the main communication, the control plane between the mobile and the MME. Obviously, there is more of the control plane, and that is in the next slide. So now looking at the second part of the control plane, that includes the MME and going all the way up to the P gateway, is that we have a control plane protocol, the GTP control, which goes between the MME and the serving gateway, and this runs on top of UDP. There's a specific port number for this GTPC, and the destination port number is 2152, which has been set aside, and GTPC is used for setting up the GTPC connection between the MME and serving gateway, and we have another GTPC connection between the serving gateway and the P gateway, and that's the one for kind of creating the S5U control plane and the user plane tunnel. So that's the overall control plane. Now looking at the user plane, the culprits here, as we know, are the mobile, the base station, serving gateway, all the way up to the end host, and somewhere over here is your internet, right? So in between your operators, packet gateway, and Aisha over here, and this is Mehmet communicating to Aisha. There is a big internet, and they are connected. So at the very top part, it's best to start from the very top, is the application which is running. So if this is Skype, this is what's running in between Aisha and Mehmet. And whatever is your application, that runs over some kind of a transport layer, and typically it's TCP or it's UDP if you're doing streaming. And then you have IP. So this is helping you to route the packet, and the packet coming from Aisha gets routed to the P gateway. That's where the P gateway advertises out to the internet, is all IP addresses in a particular subnetwork, and that subnetwork in which Mehmet belongs to should come to me, and the IP packet comes over here. Now we kind of said that this IP address of Mehmet is not topologically correct. So since it is not topologically correct, it cannot be routed over the network which is kind of sitting over here. You really just can't take this packet and put it out into this network and think that it'll bloop, come out and go to Mehmet. For that, unfortunately, you end up having to do these hacks which are called tunnels. So you kind of create a GTP tunnel for sending your packet. You take this IP packet and you put it inside another IP packet. And now this IP packet has the destination of the serving gateway. So once you put it in here, it goes out into this network. It gets routed to wherever the serving gateway is. It comes in over here to the serving gateway. He looks at this UDP. He looks at, aha, the TEID is, as we said, K. It says, oh, TIDK is for Mehmet. Oh, Mehmet is actually sitting connected to eNodeB1. So he takes this IP packet, puts it back again into another IP packet, and this time with the destination address of the eNodeB. This packet goes all the way down here, comes back here, and then he kind of looks at it. And when he looks at the GTPU header over here, he says this is TIDX. Oh, TIDX is actually for Mehmet. So he takes this IP packet, and then he knows, oh, for Mehmet, I have been calling Mehmet as my CRNTI over here, which we had said was Ashok. So this is my temporary identity that I have used between myself and the mobile. And he takes this IP packets and puts it through signaling, says that this actually packet is for Ashok, and puts it out over the air and puts it into the PDCP level, comes out, this guy says, oh, I am Ashok, this packet's intended to me, takes this packet, which is this IP packet, and then it goes all the way up to the application, the Skype, and Mehmet is able to talk. So in the reverse direction, the exact opposite kind of goes in. If he has got an IP packet, he says, oh, actually I'm called Ashok over the air, and he'll take this packet, put it in here, and the process will go around in the other way. Obviously it comes in here, then it goes down here, comes in, goes down, comes in, goes down, and then whoop, comes in and then goes up all the way to iShare. So we have a two-way communication that ends up between the two sides. And we do have a GTP primer that talks a little bit about, gives you an idea about how these GTP tunnels are set up. That pretty much completes this attach. And I know we covered quite a few things, and here are a few references to specifications that if you want to take a more deeper look into how this attach procedure is working. And if you further want more details, we have the GTP primer that talks more about how these GTP tunnels are being set up. And then we also have an S1 MME and X2 primer that kind of goes into a little bit of why SCTP is used and how this S1AP application protocol works. And then the next main video will be about the radio primer, and that's the one where we talk about how data and signaling messages are exchanged between a mobile and a base station, and from a system level perspective rather than the gory physical details. See you then. Thank you. Bye.